So calorimetry was one method we used to calculate delta H, again the enthalpies of reactions. The second and third way has to deal with Hess's law. Now one version of Hess's law we dealt with in first year chemistry, and then we've got a brand new version of Hess's law that we're going to be using. So basically what Hess's law was trying to say, and this is the version, this particular equation we used last year, where if we took the heats of formation, if that's what F stands for, of all the products, and subtract it from it the heats of formation of all the reactants, that we could figure out what the overall heat lost or gained was by a particular reaction. The other method kind of uses this idea of little intermediate steps. So if we take, for instance, path B, we could figure out the heat of this, we could figure out the heat of that, the heat of this, the heat of that, and it should be the same as if we just did path A. So let's take a look at our two versions of Hess's law. But first, kind of a few little rules and things to kind of keep in mind. When we calculate delta H, so again, delta H is enthalpies of reaction, anything in its standard state has a delta H equal to 0. So if we do this products minus reactants bit, we got to look up some values and plug it into an equation, and we'll find that anything with a delta H or anything in its elemental state will have a heat of formation of 0. We can write the formation of several compounds from their elements, and this is what we refer to as the heat of formation. What is the heat involved in creating a specific compound, whether that's NaCl or carbon dioxide or something like that. And we use the delta HF to symbolize the heats of formation. The F stands for formation, and the degrees symbol stands for standard conditions. Okay, so like I said, there's two different versions of Hess's law. One brand new to you guys, and one that should be a refresher from last year. These are kind of the steps that we take to go through Hess's law version 1. We have what is known as source reactions. So the little baby steps that we take, if we kind of jump back to here, the source reactions that I'm talking about are these. What are the intermediate steps in going from point A to point B? So we're going to take the source reactions, and we're going to set them up so they cancel, kind of like a systems of equations sort of mentality. If I multiply a source reaction, the value of the delta H for the reaction is also multiplied. And we'll do an example so you kind of see that in action. When I reverse a sign, or I reverse a reaction, then the delta H value is also switched. We will have to give you values for delta H for these source reactions, so don't worry about having to try to find those numbers. Sometimes it's easy to multiply the main reaction by a factor and then work through the problem. So we'll kind of have to go through some examples and see how that works. So let's take a look at one example right now. If you're following along in your notes packet, this is kind of below the rules for Hess's law version 2. It says example, Hess's law 2 ways. You guys are going to be calculating the delta H, the heat of combustion of methane. So you've got your overall reaction, CH4 plus 2H2O gives you carbon dioxide and water, basic combustion of methane. And the source reactions, the intermediate steps, are these three. So they'd have to kind of be given to you. We will be doing a lab where you kind of do the smaller steps and sort of prove to yourself that Hess's law should work. And then the delta H values for these particular reactions. You could look these up in a book or determine them in some other way. But these are the source reactions for my overall main reaction, which is this one right here. Okay, so what are the steps? If we think about our different rules that we have here, the first thing that we're going to do is rearrange an equation so the reactants that we want are on the right side and the products that we want are on the correct side. So I need methane on the reactant side, okay, because here's methane. So I'm going to take reaction number 1, so think about this reaction 1, 2, 3. I'm going to take reaction number 1 and flip it so that methane appears on the proper side. Notice that when I did that, what happens to my sign of delta H? As soon as I flip the reaction, the sign of delta H changes. Second thing I'm going to do, I'm not going to do anything to equation number 2 because the carbon dioxide is on the proper side. So what you're doing with these source reactions again is you're kind of comparing. So here's reaction number 2. Here's my overall goal, the products that I want, the reactants that I want. So with reaction number 2, I want the carbon dioxide on the product side, so I don't need to do anything to that equation. Third thing, I'm going to multiply reaction number 2 by 2. Not reaction number 2, reaction number 3. Change this. Reaction number 3. I'm going to multiply reaction number 3 through by 2. Why? Well, if you look at my coefficient of my equation, I need 2 waters. So how do I get 2 waters here? I'm going to multiply everything through by 2. Also notice what happens to my delta H value. If I multiply the reaction through by 2, I also have to multiply my delta H value by 2. Now finally, I'm going to add everything up and then calculate my overall heat of this reaction. You cancel out anything that is the same on both sides, and what should cancel out are the things that you don't want in your overall reaction. Things from the source reactions that aren't part of the products or the reactants. So the carbons cancel out, the hydrogen gases cancel out. What I'm left with is the methane plus 2 oxygens, gives you carbon dioxide and 2 waters, and then here is my delta H. So I just added all these things together. Now a little point of clarification. What does this negative delta H mean? Just to refresh our memories. If you have a negative delta H, that means it is exothermic. So this reaction is releasing heat, which should make sense if you think about why do we burn methane? To get heat. Let's prove it to ourselves using the second method of Hess's law. So in your notes packet, you have some steps, products minus reactants. So this would be Hess's law version 2, but here's the equation that we're using. So again, the same combustion of methane, and see if this works. We're going to look up some substances, and so this is going to be a table in the back of your book. If you haven't visited this particular appendix before, it's on page 1123. Let me get my pen working. The page 1123, very similar to a table that we used last year, but this is the one that you're going to use to look up heats of formation. So there are certain rules that kind of go along with this. As you look up values for methane, first of all, pay attention to states of matter. State of matter matters when you're looking up heats of formation. So you want to make sure that you use methane gas, carbon dioxide gas, H2O gas, because there's going to be a different value of delta H for the liquid. So pay attention to states of matter. So all of these are going to be gases. Why is O2 0? Because this is in its elemental state. And anything that is in its elemental state, I didn't mean to write delta H. Anything that is in its elemental state is going to be 0. So O2 is going to be 0. Any of those Brinkelhoff gases, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine, is going to have a heat of formation of 0. Any solid metal is also going to have a heat of formation of 0. So you'll have that table, you'll look up the numbers, and then start your calculations. So total of the heats of the products. Now here's the other thing to be careful with. What do you do with these coefficients? I have 2 moles of O2, so I'd have to multiply my O2 times 2. Well, there you go, it's 0. I have 2 moles of water, so notice that I'm multiplying the value of water by 2. Products minus reactants, P before R. So I'm plugging in my numbers, and then when you get your overall calculation, it should looking at that. It's the same as the other method. So 2 different ways to calculate enthalpy of reaction. It just kind of depends on what sort of information you have. So Hess's law version 1, Hess's law version 2. Alright, to wrap up our notes for chapter 5, since we've been talking a lot about delta H's and different heats, you're going to see a lot of different symbols. The important thing to know is that they all kind of basically mean the same thing. Your units are kilojoules per mole. The heats of formation of all, sorry, not heats of formation, the units of delta H are always kilojoules per mole. What's different for each one is just kind of the little superscripts that you see. So just to kind of, these are all the variety ones that you'll see. We've already seen F, that means formation. So use the previous slides. We kind of already talked about what those heats of formation might be. Delta H vape, this refers to vaporization, which is change of state of matter. Okay, so vaporization, you're going from the liquid to the gas. So maybe you're supposed to calculate how much heat is involved in taking water from the liquid state to the gas state. That's when you'd be calculating delta H vape. Delta H COND, this is condensation. So condensation, you're going from the gas, so let's say you've got sulfur gas, and what is the heat involved in liquefying that? So condensation is doing that change of state of matter. Delta H is combustion, and we just kind of did an example, heats of combustion. So when we did the heat of combustion of methane, when you have a delta H of combustion, it's always negative because you're always releasing heat, and it's typically a very large value. Heats of vaporization, going from a liquid to a gas, is usually going from a, like I was saying, going from a liquid to a gas, you are putting in heat. So this tends to be endothermic in nature. Going from a gas to a liquid, you're releasing heat. So these delta H values tend to be negative. Delta H, where you've got a specific compound, these are going to be your formations, heats of formations of a specific chemical. So the values that you're already looking up. So of something specific. And they could be positive and they could be negative. Most of the values that you see in the table are going to be negative. Delta H of fusion is what FUS means. And fusion is like melting point. You're going from the solid to the liquid. So going from a solid to a liquid is generally an endothermic, so you should generally see positive values for that. Delta H solid, this is your solidification. Solidification, in other words, you're freezing something. So if I was going from the, let's just use water again. Going from liquid to solid. That's why I say be careful, because state of matter matters, and this generally releases energy. Delta H sub is sublimation. So a classic example is your carbon dioxide going from a solid to a gas, sublimating. And this is going to require energy, generally speaking. Of course, there's exceptions to the rule, but I'm just sort of giving you some general signs of what's going on. Delta H sol, this means solution. So if you're dissolving something, what is the heat involved in that? So the heat in taking, for instance, calcium chloride and dissociating it and putting it in water, creating a solution, and getting calcium ions and chlorine ions. There is a heat involved in dissociating ionic compounds. And then this one we've kind of already looked at already, the delta heat of the reaction. What is the overall reaction? And when you're doing the products minus reactants is generally when we get delta H of reaction. And that can be either positive or negative. It sort of depends. Well, that is it, guys, for Chapter 5. We have lots of practice problems to work on. Be careful of those signs. If delta H is negative, it's exothermic. If delta H is positive, it's endothermic. And be careful of units. And we'll see you later.